The Software Blueprint, Mastering Estimation and Planning for Predictable Development. Chapter 1, The Crystal Ball Dilemma, Why Software Projects Struggle with Prediction. Every software project begins with a dream, a vision of a new app, a groundbreaking system, or an essential improvement. But soon after the initial excitement, a common, often daunting, question emerges. How long will this take? Or, how much will it cost? These seemingly simple questions open the door to one of the most challenging and often frustrating aspects of software development: estimation and planning. For decades, the software industry has grappled with an uncomfortable truth: we're often poor predictors of our own future. Projects consistently run over schedule, exceed budgets, or fail to deliver on their initial promises. This isn't for lack of effort or talent. It's due to the inherent complexity of software, the dynamic nature of requirements, and crucial human factors that influence our judgment. The software crisis, of missed deadlines and failed projects, isn't just a historical footnote. It's a persistent challenge that continues to plague organizations worldwide. The perils of unpredictability. Consider the tale of Project Nightingale. A mid-sized healthcare tech company embarked on a new patient portal, promising a rollout in 6 months. The initial enthusiasm was palpable. Engineers worked long hours, the project managers diligently tracked tasks, and executives eagerly awaited the launch. Yet, as the 6-month mark approached, only a fraction of the promised features were ready. Dependencies that seemed minor became bottlenecks, user feedback demanded significant rework, and the initial architectural choices proved more limiting than anticipated. The 6-month estimate stretched to 9, then 12, then 15. Costs spiraled, key personnel burnt out and left, and ultimately, a much scaled-down version was begrudgingly released almost 2 years after the initial projection, having cost 3 times its original budget. Project Nightingale isn't an anomaly. It's a common narrative across industries. Studies by organizations like the Standish Group, which have tracked project performance for decades, consistently show that a significant percentage of software projects are challenged, late, over budget, or with reduced features, or outright fail. While the exact numbers vary year to year, the underlying pattern remains. Predicting and delivering software successfully is very hard. Why is software different? The core challenges. So, what makes software, in particular, such a notoriously difficult domain for estimation compared to, say, building a house or manufacturing a car? Invisibility and intangibility. Unlike physical artifacts, software is inherently invisible. You can't touch it, hold it, or easily see its internal mechanisms. This makes it difficult to conceptualize, measure, and even communicate its exact scope. A house has visible walls, a roof, plumbing. Software has lines of code, algorithms, and data structures that are only visible to those who understand its logical construction. Complexity and interdependencies. Software systems are incredibly intricate networks of logic, data, and interactions. A small change in one part of the system can have unforeseen ripple effects elsewhere, like pulling a single thread in a complex tapestry. The number of possible states, inputs, and interactions often grows exponentially, making it impossible to foresee every scenario. Unique, not repetitive builds. While some components might be reused, e.g., libraries, frameworks, large-scale software projects are rarely identical replicas of previous ones. Each new system often addresses a unique problem, integrates with new environments, or pushes the boundaries of existing technology. It's like building a custom, never-before-seen machine every time, rather than assembling cars on an established production line. Evolving requirements. Requirements are rarely static. As a project progresses, stakeholders gain new insights, market demands shift, and early assumptions are validated or invalidated. What seemed clear at the outset might become ambiguous or even obsolete midway through development. This moving target phenomenon makes early, fixed estimates extremely risky. Human factors and productivity variance. Software development is a highly creative and intellectual endeavor. A great developer might be 10 times more productive than an average one. Mood, team dynamics, interruptions, and individual skills significantly impact output. This human variability is incredibly difficult to quantify and factor into an upfront estimate. Hidden unknowns and unknown unknowns. This is perhaps the most insidious challenge. We can list known tasks, and we can anticipate some known risks. But every project contains elements we don't even know we don't know. Unexpected technical hurdles, integration nightmares, or unforeseen regulatory changes. These unknown unknowns are the true project assassins, emerging suddenly to derail schedules and budgets. The high cost of poor estimates. When projects frequently miss their marks, the consequences are severe, far beyond just a rejuggled timeline. Missed market opportunities. Being late means competition can capture market share or a product's relevance diminishes. Budget overruns. Every delayed day or every additional feature adds to labor costs, infrastructure expenses, and licensing fees, often jeopardizing profitability. Damaged reputation and lost trust. External stakeholders, clients, investors lose faith, and internal stakeholders become skeptical. This erosion of trust can damage future collaborations. Team burnout and low morale. Constantly chasing unrealistic deadlines leads to stress, demotivation, reduced quality, and high employee turnover. Reduced quality. Rushed work often leads to shortcuts, sacrificing robust architecture, thorough testing, and user experience for the sake of artificial deadlines. Political fallout. Internally, missed targets can lead to blame games, strained departmental relationships, and even job losses. The benefits of striving for better predictability. While perfect prediction is unattainable, a persistent effort to improve estimation and planning yields immense benefits. Enhanced decision-making. More reliable estimates allow leadership to make informed choices about investments, resource allocation, and strategic direction. Improved trust and transparency. When you can predictably deliver on commitments, trust flourishes among teams, stakeholders, and customers. Stable and motivated teams. Clear plans and realistic expectations reduce stress, fostering higher quality work and a healthier team environment. Efficient resource utilization. Accurate forecasts help allocate people, time, and money where they are most needed, minimizing waste. Early risk mitigation. The very act of estimating and planning reveals potential problems and dependencies early, allowing proactive mitigation. Smoother deliveries and hitting market windows. Projects are more likely to launch on time, capitalize on market opportunities, and achieve their business goals. This book is founded on the premise that while we can't eliminate uncertainty, we can certainly manage it better. We can equip ourselves with tools, techniques, and a mindset that transforms the murky crystal ball into a clearer lens. We can move from reactive firefighting to proactive navigation. In the following chapters, we'll peel back the layers of this dilemma, starting with the most unpredictable element of all, the human mind. Chapter 2, The Human Factor, Psychology, Bias, and Expert Judgment. Before we dive into techniques and numbers, it's crucial to acknowledge the most complex variable in any estimation equation. The human being. Software estimation, at its heart, is a human activity. It's people, often smart, experienced, and well-intentioned people, who create these predictions. And as humans, we are all susceptible to cognitive biases, unique experiences, and a range of emotions that can profoundly sway our judgment. The peril of optimism bias. It'll be done by Friday. One of the most pervasive and insidious biases in estimation is optimism bias, often referred to as the planning fallacy. This is our inherent tendency to be overly optimistic about our own abilities and future outcomes, especially regarding tasks we are responsible for. We tend to underestimate the time, cost, and risks involved while overestimating the benefits. Think back to a time you gave an estimate for a task you were excited about. Perhaps you thought, oh, that's just a quick 5-minute fix, only to discover an hour later you're still debugging it. Or, I can definitely finish this module by the end of the week, only for unexpected blockers to push it into the next. This isn't laziness, it's a deeply ingrained psychological quirk. We tend to focus on the best-case scenario, overlook past similar failures, and discount the possibility of unforeseen complications. Anecdote. The website recode that wouldn't end. Sarah, a senior developer, was tasked with recoding an old client website. "It's just a front-end refresh," she confidently told her manager. I can probably knock it out in 2 weeks, maybe 3 tops if there are any tricky responsive issues. Sarah was highly skilled, and the task seemed straightforward. The optimism was palpable. She focused on her past successes and the seemingly simple nature of the cosmetic changes. However, she quickly encountered problems. The old codebase was far messier than anticipated, filled with spaghetti code and undocumented dependencies. The client's content management system, initially thought to be a minor integration, had quirky, undocumented APIs. Her email inbox exploded with unrelated technical support requests, constantly pulling her away from focused work. The 2 to 3 weeks turned into 6, then 8, then 10. Sarah, despite her expertise, had fallen victim to optimism bias, failing to account for the true complexity of the legacy system and the daily distractions of her role. Her initial assessment of the scope was correct, but her estimation of the effort required within real-world constraints was tragically flawed. Other cognitive biases that skew estimates: anchoring effect. We subconsciously rely too heavily on the first piece of information offered, the anchor, even if it's irrelevant. For example, if a manager casually suggests, "Can this be done in 2 weeks?" Even if it's an arbitrary number, it can become an unconscious anchor for the team's subsequent estimate. Your estimate might then be 2.5 weeks, when a truly independent assessment might logically lead to 6. The initial number provided sets a skewed frame of reference. Confirmation bias. Once we have an initial estimate or a belief about how long something will take, we tend to seek out, interpret, and remember information in a way that confirms our existing belief. We might selectively recall positive past experiences and conveniently forget the difficult, slow-going ones that lasted far longer than anticipated for a similar task. Sunk cost fallacy. This bias describes our tendency to continue investing in an endeavor, time, money, effort, if we've already invested heavily in it, even when new information indicates it's a poor investment. This can lead to continuing to underestimate the effort needed to finish a failing module or feature, rather than critically reevaluating whether to abandon or significantly alter it. Hindsight bias. I knew it all along. After a project runs over time, it's easy to look back and say, "We should have seen that coming." This bias can make us overconfident in our future predictions, mistakenly believing that past failures were easily foreseeable. It obscures the true unpredictability that existed at the time of the original estimate. Availability heuristic. We overestimate the likelihood or importance of events that are easier to recall from memory. If a new technology recently caused a major security breach on a different project, we might overestimate its potential impact on our current project's timeline, even if the contexts and risks are different. Conversely, if a task once went unusually smoothly, we might use that as our mental reference point, ignoring the more common, difficult experiences. The power of expert judgment and its limits. Despite the biases, expert judgment remains a cornerstone of good estimation. Experienced developers, architects, and project managers often have an intuitive sense of how long something feels. They draw upon a vast mental database of past projects, challenges, and solutions. Their brains are highly tuned pattern recognizers. The brain as a pattern recognizer. An expert's brain quickly maps a new problem to similar ones encountered before, providing a rapid, almost subconscious estimate. This is often why a 5-minute conversation with a seasoned veteran can yield a surprisingly high-level estimate that is often directionally accurate enough for early planning. However, expert judgment isn't foolproof. It carries its own set of limitations. The guru problem, over-reliance on a single expert, can introduce a significant bottleneck and amplify their individual biases. If the expert is overly optimistic, burnt out, or politically protected, their estimate can dangerously underrepresent the true effort required. What happens if the guru leaves or gets sick? Context matters. An expert's experience might be specific to certain technologies, team sizes, organizational cultures, or project types. Applying that experience blindly to a drastically different context can lead to gross inaccuracies. For example, an expert in mobile app development might dramatically misestimate a complex embedded systems project. Difficulty communicating the why? Experts often struggle to articulate why they arrived at a certain number. Often, their judgment is based on years of internalized experience, making it hard to express the underlying assumptions, risks, and reasoning. This makes it difficult for others to understand, challenge, or learn from their estimates, hindering team growth and shared ownership. Techniques to mitigate bias and leverage judgment wisely. Recognizing these human tendencies is the first, crucial step. The next is to employ strategies that counteract them, transforming subjective guesses into more robust, informed predictions. Group estimation: don't rely on a single expert. Actively seek out multiple perspectives. Techniques like planning poker, which we'll explore in Chapter 5, or the wideband Delphi method, detailed in Chapter 6, are specifically designed to leverage collective intelligence and force honest discussion about differing viewpoints. When people estimate in isolation, biases are more pronounced. In a group, diverse perspectives can challenge assumptions and surface hidden complexities. Anonymous estimation. Providing estimates anonymously can significantly reduce pressure from hierarchy, team politics, or dominant personalities. This encourages participants to provide more honest and less biased input, as they are not fearing immediate reprisal or judgment for being perceived as too high or too low. Break down the work. Large, daunting tasks are magnets for optimism, bias, and uncertainty. Our brains struggle to estimate grand, nebulous concepts. By breaking down the work into smaller, more manageable units, tasks that are less ambiguous and more concrete, they become significantly easier to estimate accurately. This process of decomposition is a fundamental skill we will revisit. Reference past data actuaries, not prophets. Instead of just relying on gut feeling, rigorously look at how long similar tasks actually took in the past. This provides a crucial reality check and helps counter optimism bias by grounding estimates in empirical evidence. This is the foundation of techniques like analogy-based estimation and velocity-driven forecasting. True estimation is less about prophetic foresight and more about actuarial science. Use three-point estimation. Instead of just a single number, ask for a best-case, optimistic, worst-case, pessimistic, and most likely estimate for each task. This forces the estimator to explicitly think about potential risks and uncertainties, which are often glossed over in single-point estimates. This approach provides a realistic range rather than a deceptively precise point. Question assumptions. Explicitly list and challenge every assumption underpinning an estimate. For instance, for this feature to take 2 weeks, we assume the API documentation is accurate, the third-party service is stable, and John will be available to help. What if these assumptions don't hold true? Making assumptions explicit allows them to be validated, challenged, or turned into risks that can be tracked. Foster a culture of psychological safety. Teams must feel safe to provide honest, even pessimistic or uncomfortable, estimates without fear of reprisal, judgment, or being seen as negative. Leaders and managers must understand that bad news about a deadline is always preferable to hidden problems that only surface when it's too late. A transparent, blame-free environment encourages realistic assessments, not just what management prefers to hear. Understand the ask. Before anyone estimates, the entire team must have a shared, crystal-clear understanding of what needs to be built and why. Ambiguity is fertile ground for wildly inaccurate estimates, as different people will be estimating different things in their heads. Invest time in clarifying requirements, asking probing questions, and confirming mutual understanding. By understanding the psychological quirks that influence our judgment, and by actively implementing techniques that mitigate bias and foster collaborative, data-driven assessment, we can transform estimation from a hopeful guess into a disciplined and much more accurate process. This human awareness is the bedrock upon which all effective estimation and planning methods are built. In the next chapter, we will establish the fundamental building blocks of what we're actually trying to measure. Chapter 3: Foundations. What are we really estimating? Before you can estimate anything effectively, you need to be crystal clear about what you're estimating. Is it time, money, effort, scope? The confusion between these terms is a common pitfall leading to miscommunication and flawed expectations. This chapter will define these fundamental concepts and introduce the critical idea that estimates are not static, they change and refine over time. Defining the core concepts. Imagine you're planning a journey. You wouldn't just say it's far, you'd specify if you mean distance, trip duration, or fuel cost. Similarly, in software, we need precise language to avoid misinterpretations. Scope. What are we building? Definition. Scope defines the boundaries of the project or a specific feature. It outlines what work needs to be done and, equally important, what does not. It includes the features, functionalities, user stories, non-functional requirements like performance, security, and usability, and all deliverables. Importance, often the most overlooked element of estimation, yet it's the foundation. Without a clear and stable scope, any estimate of effort or duration is built on quicksand. The dreaded scope creep, the gradual, uncontrolled expansion of requirements during a project, is a primary cause of blown budgets and extended timelines. Without a well-defined boundary, it's impossible to measure the territory. Measurement, quantified by the number of features, user stories, use cases, or requirements. This is often initially qualitative, but as you break down work, it becomes more tangible and measurable. Effort, how much work? Definition. Effort refers to the actual work required to complete a task or a set of tasks. It's the total amount of person hours, person days, or person weeks needed, irrespective of how many people are working on it simultaneously. Analogy. If it takes one person 8 hours of focused, uninterrupted work to paint a fence, the effort is 8 person-hours. If 3 people work together on it, the effort is still 8 person-hours, though the duration would decrease as they're working in parallel. Importance, this is the base unit for many estimation techniques. It helps in resource allocation, understanding the true size of a task, and translating to cost calculations. Measurement. Hours, days, ideal days, or abstract units like story points, discussed in later chapters. Duration, how long will it take? Definition. Duration is the actual calendar time from start to finish for a task, a phase, or an entire project. Influencing factors. Duration is derived from effort, but is also heavily influenced by external factors that reduce the amount of actual work time available. These include available resources. How many people are working on it and how available are they, e.g., full-time versus part-time, vacation schedules. Parallelization. Can tasks be done simultaneously or must they be done sequentially? Dependencies. Are there external factors, other teams, or preceding tasks that must be completed first? Interruptions. Meetings, other projects, unplanned urgent work, daily office distractions. Team efficiency. The overall speed, skill, and effectiveness of the team. Importance. This is usually what stakeholders care about most. When will it be ready? Measurement. Calendar days, weeks, months. Cost, how much money? Definition. The total financial expenditure required to complete the project or a specific component. Components. Primarily driven by effort, labor costs. Salaries, benefits, overhead, but also includes software licenses, hardware, infrastructure, e.g., cloud services, third-party services, training, and contingency budgets for unforeseen issues. Importance. Crucial for budgeting, financial approval, business case analysis, and demonstrating return on investment. Measurement. Currency, e.g., dollars, pounds, euros. Resources, who and what? Definition. The people, tools, equipment, or materials necessary to perform the work. Types. Developers, quality assurance engineers, designers, project managers, specific software and hardware tools, testing environments, external data sources, third-party libraries. Importance. Directly impacts duration and cost. Unavailable, insufficient, or inappropriate resources can significantly delay a project or inflate its cost. Units of estimation. From concrete to abstract, how do we express effort or size in a way that is useful for estimation? There are several common units, each with their pros and cons, and best used in specific contexts. Hours, days, concrete time. Pros, familiar, intuitive, and seemingly easy to translate to cost. Managers and clients often request these units because they get them immediately. Cons, highly susceptible to the optimism bias discussed in Chapter 2. Assumes perfect, uninterrupted work, which rarely happens in a real office environment. Ideal time versus calendar time. doesn't fully account for complexity or individual skill differences. An hour for me might be 3 for you, for the same task. When to use? Best for very small, well-understood tasks by individuals, e.g., a known bug fix that has clear steps, or when converting abstract estimates to a fixed timeline very late in the planning process after significant discovery. Ideal days hours. Pros. Attempts to account for the reality of interruptions by defining an ideal working day, e.g., 6 hours of focused work, not 8 hours, acknowledging meetings, breaks, and context switching. Useful for estimating individual focused effort. Cons, still prone to optimism, difficult to align across different individuals' definitions of ideal. My ideal day may still differ from yours. When to use? Can be used internally within a team that has a shared, empirically derived understanding of what an ideal day entails for them. Story points, abstract relative. Pros. Focuses on relative complexity, effort, and uncertainty, rather than absolute time. Less prone to optimism bias because you're comparing one task to another, not guessing a future date. Promotes team collaboration and discussion, leading to shared understanding. Excellent for Agile environments. Cons, not intuitive for external stakeholders or those new to Agile. Requires calibration within a team. A 5-point story for one team has no inherent meaning for another. Cannot be directly converted to calendar time without a historical velocity metric, covered in Chapter 5. When to use? The primary unit for Agile teams for sizing user stories and features during iterative development. T-shirt sizes, S, M, L, XL, abstract relative. Pros, very quick, high-level estimation. Excellent for early, fuzzy project stages when detail is scarce. Promotes rough relative sizing without getting bogged down in numbers. Useful for filtering out items that are too big without further breakdown. Cons. Lacks granularity for detailed planning. Can be overly simplistic and lead to broad interpretations if not calibrated within a team. When to use? For initial road mapping, portfolio planning, or when requirements are extremely vague and you just need a rough order of magnitude to prioritize. The cone of uncertainty, estimates evolve. One of the most critical concepts in software estimation is the cone of uncertainty, a model describing how the accuracy of project estimates improves over time as more information is known. This principle states that at the very beginning of a project, the uncertainty around its scope and solution is very high. Consequently, initial estimates will have a very wide range of possible outcomes. As the project progresses and more is learned, uncertainty decreases, and the estimates become significantly more accurate and precise. Imagine a cone lying on its side, wide at the left and narrow at the right. At its wide, open base are the early days of a project. You might have an idea, a vision, but many unknowns. You might estimate a project could take 100 days, but at this stage, the actual outcome could realistically be anywhere from 33 days to 300 days, a range of plus or minus 200%. This is often referred to as the fuzzy front end of a project. As you move towards the cone's narrow tip, closer to project completion, solutions are built, tested, and refined, and the range of possible outcomes shrinks dramatically, perhaps to plus or minus 5 to 10%. Phases of the cone, typical project lifecycle example. Concept vision. Estimate accuracy plus or minus 100 to 200%. Your initial idea is still abstract, and you barely know what you're truly building or how. Requirements exploration. Estimate accuracy plus or minus 50 to 100%. Some clarity emerges, but still many unknowns about implementation details. Architecture design. Estimate accuracy plus or minus 25 to 50%. The technical path is becoming clearer, but detailed challenges may still be hidden. Detailed design development, mid-project. Estimate accuracy to 25%. Most major components are understood and development is underway. Testing deployment, near end. Estimate accuracy plus or minus 5 to 10%. Fine-tuning and minor issues remain, but the bulk of the work is done. Implications of the cone for estimation. Don't ask for precise estimates early. It's futile and misleading. A precise number very early on is often a lie, even an unintentional one, as the information simply isn't available to support it. Instead, ask for and provide a range. We estimate this could take between 3 and 9 months. Embrace iteration and learning. Don't hold a team rigidly to an early, high uncertainty estimate. Instead, use that early broad estimate to decide if the project is worth exploring, and then commit to refining it as information becomes available through iterative development cycles. Invest in learning. The fastest way to narrow the cone is to learn more through prototyping, detailed analysis, user feedback, technical spikes. Small experiments to reduce technical unknowns, and continuous discovery. Communicate the range transparently. Be honest and transparent with stakeholders about the inherent uncertainty at different stages. Frame estimates as probabilities or ranges. At this stage of discovery, we believe it will take between X and Y months, with an 80% confidence level. Breaking down work, the art of decomposition. Estimating a massive, monolithic project like build a new e-commerce website is like trying to guess the weight of an invisible elephant. It's too big, too abstract, and too overwhelming for the human mind to grasp granularly. The fundamental key to effective estimation, regardless of the technique used, is to break down the work into smaller, more manageable pieces. This process is called decomposition. Work breakdown structure, WBS. A hierarchical decomposition of the total scope of work to be carried out by the project team to accomplish the project objectives and create the required deliverables. It starts with the major deliverables or project phases and progressively breaks them down into smaller, more definable work packages, right down to individual tasks. Example, simplified e-commerce website WBS to illustrate layers. E-commerce platform, major deliverable. A user management module, subsystem. 1. Login logout functionality, feature. 2. User registration, feature. 3. Profile management, feature. A. Implement user profile page, sub-feature work package. B. Add edit profile functionality, sub-feature work package. C. Integrate profile data persistence, task. B. Product catalog module. 1. Product display. 2. Search and filter. 3. Product details page. II. Admin panel, major deliverable. A. Order management. B. User analytics. III. Deployment, major deliverable. A. Server setup. B. Database migration. User stories, Agile context. In Agile development, features are often expressed as user stories from the perspective of the end user. They follow a simple format. As a type of user, I want some goal so that some reason benefit. Example, as a registered user, I want to be able to reset my password so that I can regain access to my account if I forget it. Benefit for estimation. User stories are typically small enough to be understood and estimated by a development team. They focus on delivering user value rather than just technical tasks. When a story is too large to estimate confidently, it's a signal to break it down into smaller, more manageable stories. By clearly defining what we're estimating, scope, effort, duration, cost, resources, choosing the right units of measurement for the context, understanding how estimates naturally refine over time, and diligently breaking down complex work, we lay a solid foundation for more accurate and reliable predictions. These foundational principles underpin all successful estimation approaches, whether traditional or agile. In the next chapter, we'll start exploring the specific techniques, beginning with established traditional methodologies. Chapter 4. Traditional approaches, Function Points, PERT, and CPM. Before the widespread adoption of Agile practices, traditional project management methodologies, often characterized by sequential phases, e.g., waterfall, developed robust techniques for estimation and planning. These methods typically involve a more upfront, detailed analysis and are well suited for projects where requirements are stable and the scope is well defined from the outset. While Agile approaches often dominate today's discourse, understanding these traditional methods provides valuable insight and can still be highly effective for certain types of projects or specific stages. Function point analysis. Measuring what not how. Function point analysis, FPA, is one of the most established and widely recognized techniques for estimating the size of a software system. Unlike estimating by lines of code or hours, FPA measures the functional user requirements of a system from the user's perspective. independent of the technology or programming language used. It measures the what, the functionality delivered, rather than the how, the implementation details of that functionality. Think of it like this. If you're building a car, FPA wouldn't count the rivets or the bolts. It would count the number of seats, the type of engine, the navigational features, and the safety systems, essential things the user experiences and interacts with. Core idea. Break down the system into measurable function points based on 5 standard component types, categorized by how data moves in or out of the system or is stored internally. Internal logical files, ILF. User-identifiable logical data or control information maintained within the boundary of the application itself. Example, a customer database and order history file. External interface files, EIF. User-identifiable logical data or control information referenced by the application but maintained by another application. Example, data from an external CRM system, a third-party payment gateway's transaction logs. External inputs, EI, elementary processes that process data or control information coming from outside the application boundary. Example, a user submitting a login request, an administrator adding a new product via a form. External outputs, EO, elementary processes that send data or control information from inside the application boundary to outside. Example, generating a sales report, displaying search results, printing a receipt. External inquiries, EQ, elementary processes that retrieve data or control information and present it to the user through specific inquiries, without altering internal data. Example, searching for a product in a catalog, checking an account balance. How it works, simplified overview. Identify and count components. A trained function point analyst identifies all instances of these 5 component types within the system's requirements. Assign complexity. Each identified instance, e.g., each external input, is rated for its inherent complexity, low, average, or high, based on predefined rules concerning the number of data elements and logic involved. This rating assigns a specific number of unadjusted function points to that component. Apply value adjustment factors, VAF, a set of 14 general system characteristics, e.g., data communication, distributed processing, performance, reusability, operational ease, are assessed for their overall influence on the project effort. This assessment generates a total value adjustment factor, typically ranging from 0.65 to 1.35. Calculate adjusted function points. The sum of the unadjusted function points is then multiplied by the value adjustment factor to get the final adjusted function points. This is the ultimate size measure of the software. Converting function points to effort cost. Once you have the software size in function points, you can use historical data from previous projects to correlate function points with effort, person hours, days, or cost. For example, an organization might have learned that, on average, they deliver X person hours of effort per function point, or Y dollars per function point. This historical data provides a realistic basis for future estimates. Pros of FPA, technology independent. Estimates are independent of the specific technology stack, programming language, or even the skills of the development team. Early estimation capability can be performed early in the project lifecycle, as soon as functional requirements are reasonably stable, even when detailed design isn't yet available. Transparency and auditability provides a structured, objective, and auditable measure of software size, reducing ambiguity. Baseline for comparison allows for consistent comparison between different projects or even benchmarking against industry averages, helping to assess productivity. Cons of FPA requires training, can be complex and requires trained, certified analysts to apply consistently. Perceived bureaucracy can feel heavy and time-consuming, especially for smaller or agile projects where speed and adaptability are prioritized. Primarily functional. While it does address some non-functional aspects via the value adjustment factors, its core focus is on functional scope. It's less effective for projects driven heavily by non-functional requirements like security or performance optimization alone. Subjectivity in counting. Despite rules, different analysts might count components slightly differently, leading to variations. When to use. Best suited for large, well-defined projects, e.g., enterprise resource planning systems, large financial applications, where a stable baseline of requirements is crucial, and for portfolio-level sizing, benchmarking, and external contracting scenarios. Program Evaluation and Review Technique, PERT, probabilistic estimation. PERT is a project management technique that arose from complex defense projects where activity durations were highly uncertain. It's designed to analyze and represent the tasks involved in completing a project, particularly when the time taken for each task is variable. It offers a systematic way to deal with this variability by using a statistical approach rather than a single definitive number. Core idea: instead of just providing a single, best guess estimate for a task, PERT uses 3-time estimates for each activity to capture the range of uncertainty. Optimistic time, O. The shortest possible time to complete the activity, assuming everything goes perfectly and no unexpected problems occur. This is your best-case scenario. Most likely time, M. The most realistic time estimate, considering typical circumstances, normal disruptions, and the usual efficiency of the team. This is what you would expect to happen. Pessimistic time, P. The longest possible time to complete the activity, considering potential significant delays, unforeseen difficulties, and worst-case scenarios, excluding catastrophic, extremely rare events. Calculating expected time, TE. PERT uses a weighted average formula to calculate the single expected time for each activity, giving more weight to the most likely estimate. TE equals optimistic plus 4 times most likely plus pessimistic, /6. Example: if O equals 2 days, M equals 3 days, P equals 10 days, indicating a high degree of uncertainty if things go wrong, then TE equals 2 plus 4 /3 plus 10, /6 equals 2 plus 12 plus 10, /6 equals 24 /6 equals 4 days. Calculating variance, sigma 2. PERT also provides a way to quantify the range of uncertainty around the expected time for each activity, which is crucial for understanding overall project risk. Sigma 2 equals pessimistic optimistic, /6 Example continued. Sigma 2 equals 10 /6 equals 8 /6 2 equals 1.33, 2 approximately 1.78. A higher variance means more uncertainty. Project duration. Once you have the expected times for all individual activities, they can be used in conjunction with critical path method, discussed next, to determine the overall project duration. The variances of activities along the critical path are summed to calculate the project's overall variance. This allows project managers to use statistical methods to estimate the probability of completing the entire project by a certain deadline. For instance, you could calculate there's an 80% chance of finishing by X date. Pros of PERT: accounts for uncertainty, directly incorporates risk and variability into estimates, providing a more realistic outlook than single-point estimates. Provides a range, offers a more nuanced perspective on possible outcomes rather than a false sense of precision. Statistical basis, allows for probabilistic calculations for project completion dates, aiding risk assessment. Forces consideration of extremes, encourages teams to think through best and worst-case scenarios, revealing potential issues that might otherwise be overlooked. Cons of PERT: subjectivity of estimates. The O, M, P estimates, while structured, are still subjective guesses. The quality of the output depends on the quality of these initial inputs. Complexity can be more time-consuming and conceptually complex to apply, especially for projects with a very large number of detailed tasks. Assumes independence. Assumes that the completion times of individual tasks are independent, which is rarely perfectly true in complex, interactive software projects. When to use. For projects with a significant amount of uncertainty, particularly in research and development, innovative projects, or when specific activities have high inherent risk and you need a robust, probabilistic forecast of project completion. Critical path method, CPM, identifying the longest path. Emerging around the same time as PERT, the critical path method, CPM, is a powerful technique for project scheduling that focuses on identifying the longest sequence of dependent tasks, known as the critical path. Any delay in a task on this path will directly delay the entire project. Core idea: CPM helps project managers determine the shortest possible time to complete a project and identify which tasks are critical, meaning they cannot be delayed without delaying the entire project, and which have slack, meaning they can be delayed without affecting the overall project completion date. How it works: list all activities, identify every distinct task required to complete the project, usually derived from a work breakdown structure, WBS. Determine dependencies. For each task, define which other tasks must be completed before it can begin. For example, you can't test a module before it has been developed. Estimate activity durations. Assign a single-point estimate for the expected duration of each task. This could be a fixed number of days or the expected time, TE, calculated using PERT. Draw network diagram. Create a visual representation of tasks and their dependencies, typically using a network diagram where nodes represent tasks and arrows represent the flow and dependencies. Calculate all paths. Trace all possible sequences of tasks from the project start to the project end. Identify the critical path. The path with the longest total duration through the network diagram is the critical path. If any activity on this path takes longer than estimated, the entire project will be delayed by at least that much. Identify slack, float. Activities not on the critical path often have slack or float, meaning they can be delayed by a certain amount without affecting the overall project duration. This insight allows for flexible resource allocation and risk management. Benefits of CPM: clear project duration, provides a reliable estimate of the earliest possible project completion date, assuming current estimates and dependencies hold. Focus on critical tasks, helps managers prioritize and closely monitor the tasks that are absolutely crucial for staying on schedule. This enables proactive management of potential bottlenecks. Identifies bottlenecks, highlights specific tasks or sequences of tasks that could become roadblocks for the project. What if analysis allows managers to assess the impact of potential delays or accelerated efforts on the critical path and overall project timeline. For example, what if task X takes twice as long? How does that impact our deadline? Cons of CPM: assumes fixed durations. Traditionally, CPM uses single-point estimates for task durations, not explicitly accounting for variability as well as PERT. Its accuracy depends heavily on the reliability of these initial estimates. Doesn't account for resource constraints. The basic CPM model assumes that all necessary resources, people, equipment, will be available when needed. In reality, resource contention can significantly alter the critical path and project duration. Requires clear dependencies. Can be challenging to accurately map all dependencies in highly complex or rapidly evolving software projects. Dynamic nature. The critical path can shift as the project progresses if tasks take longer or shorter than expected, or if dependencies change. This requires regular updates and recalculations. When to use. For projects with clearly defined tasks, dependencies, and relatively stable scope. Particularly when precise scheduling and deadline management are paramount, such as fixed-price contracts, regulatory compliance projects, or projects with extensive hardware or external system dependencies. CPM is a common feature within most project management software tools. The role of traditional methods in modern software development. While Agile approaches often emphasize iterative planning and adaptability, the principles behind traditional methods remain incredibly valuable. They are not obsolete, but rather offer a different lens through which to view project planning. Initial feasibility and large projects. For very large-scale, strategic projects, a high-level function point analysis or a combined PERT CPM analysis can provide an initial sanity check, a strategic baseline, and a robust justification for investment before diving into Agile sprints. Hybrid approaches. Many organizations effectively use a hybrid approach, employing elements of traditional planning for longer-term roadmaps, e.g., a high-level WBS for major releases or product versions, and Agile techniques for daily execution and detailed planning within shorter sprints. This allows for both long-term vision and short-term adaptability. Understanding fundamentals. The core concepts of identifying scope, breaking down work, understanding dependencies, and managing risk are universal to all project management. Traditional methods provide a foundational and often rigorous understanding of these principles, which can then be applied or adapted within any methodology. By leveraging these time-tested techniques, project managers can gain a deeper understanding of project scope, risks, and timelines, facilitating more robust and defensible estimates, especially in environments that demand greater upfront predictability. In the next chapter, we'll shift our focus to the dynamic and iterative world of Agile estimation, exploring how it tackles uncertainty through relativity and continuous feedback. Chapter 5: Agile Estimation. Story points, velocity, and iterative planning. As software development evolved, particularly with the advent of the Agile Manifesto in 2001, a new philosophy for managing projects emerged. This philosophy questioned the very premise of detailed upfront planning and fixed single-point estimates in highly uncertain environments. Agile estimation embraces change, collaboration, and iterative refinement, fundamentally altering how we approach the notoriously difficult task of predicting software development. The Agile shift: embrace change, deliver value. Traditional methods, with their emphasis on fixed plans and detailed upfront estimates, often struggled with the fluid reality of software projects. The world doesn't stand still while a project progresses. Requirements shift, market conditions change, and new technical insights emerge. The Agile Manifesto's core values: responding to change over following a plan, and individuals and interactions over processes and tools, led to a different approach to estimation. Key principles that distinguish Agile estimation: iterative and incremental. Estimates are not set in stone at the beginning of a multi-year project. Instead, they are continuously refined and revisited during short, repeating development cycles, often called sprints or iterations. This means you estimate in smaller chunks as you go. Relative sizing, not absolute time. This is a crucial distinction. Instead of guessing hours or days for new, uncertain tasks, Agile teams primarily focus on how large one piece of work is relative to another. This inherently acknowledges the difficulty of precise time estimations. Collaborative and consensus-driven. Estimation is not a top-down directive or an individual's pronouncement. It's a team activity, fostering discussion, shared understanding, and collective ownership of the numbers. Just-in-time estimation. Detailed estimation is done for work that is next up, e.g., for the upcoming sprint, while future work receives higher-level, less precise estimates. This aligns with the cone of uncertainty, Chapter 3, acknowledging that detailed estimates early are inherently inaccurate. Value-driven. The focus shifts from delivering a predetermined scope, often fixed early on, to delivering the most valuable features in a given timeframe, adapting the scope as understanding evolves. Story points, a unit of relative size. Story points are the most common unit of estimation in Agile. They are not a measure of time. They are an abstract measure of the relative effort required to implement a user story or feature. This effort typically accounts for a combination of factors: complexity, how intricate or difficult is the underlying logic or problem being solved? Is it straightforward or full of tricky edge cases? Uncertainty risk. How many unknowns are there? Is the team familiar with the technology, domain, or integration partners? How much research or spike work might be needed to reduce risk? Effort, volume of work. How much actual work, coding, testing, design, deployment activities, documentation is involved? Why relative sizing? Humans are generally better at relative sizing than absolute sizing when faced with inherent uncertainty. Think about it, it's far easier to say, a dog is bigger than a cat, but smaller than an elephant, than it is to guess the exact weight of each animal without a scale. Similarly, in software, this user story feels twice as big as that one, is often more accurate and less susceptible to the optimism bias, Chapter 2, than trying to pin down exact hours. Relative estimates help teams focus on the proportions of effort rather than getting caught up in the impossibility of predicting calendar clock time in a volatile environment. The Fibonacci sequence and variations. Agile teams often use a modified Fibonacci sequence for story point values, e.g., 1, 2, 3, 5, 8, 13, 21, etc. Rationale. The increasing gaps between numbers, e.g., the jump from 8 to 13 is larger than 1 to 2, are intentional. They reflect the increasing uncertainty as tasks get larger. When a team estimates a small task, they can be fairly precise. But for larger tasks, the level of unknown factors makes a precise number misleading. The Fibonacci sequence forces people to decide if a task is a bit bigger or much bigger, avoiding artificial precision for large items. If something is larger than a 13, it's often a signal that it needs to be broken down further. Example, conceptual. A 1 might be a very small, simple content change. A 3 might be a straightforward login feature for an existing user. An 8 could be integrating with a new, well-documented payment gateway. A 21 would typically indicate a massive, highly complex feature that absolutely needs further analysis and breakdown before it can be estimated in detail. Calibration. Story points acquire meaning through calibration within a specific team. A team will agree on a baseline story, e.g., a 3-point story is something like adding a new field to a form and displaying it. All other stories are then estimated relative to that baseline story and to each other. This calibration happens over time as the team completes work and gains experience. Crucially, this means that a 5-point story for Team A might represent a different amount of estimated effort than a 5-point story for Team B due to different skill sets, tools, or domain knowledge. Therefore, you cannot compare story point estimates directly between different teams. Planning poker, a collaborative estimation technique. Planning poker is the most widely adopted, particularly in Scrum, technique for group estimation using story points. It is designed to foster consensus, expose assumptions, and leverage the collective intelligence of the development team. How it works. Attendees: the product owner, who explains the user story, the Scrum Master, who facilitates the session, and the entire development team, who will do the actual estimation. Story explanation. The product owner reads a user story, or a small feature description, and clarifies any questions the team has about its scope, requirements, or desired outcome. This discussion is critical for ensuring everyone has a shared understanding. Silent estimation. Each team member privately chooses a card from their planning poker deck representing their story point estimate using the chosen sequence, e.g., Fibonacci numbers. Simultaneous reveal. All team members reveal their chosen cards simultaneously. This prevents anchoring, Chapter 2, where early estimates can unduly influence others. Discuss and re-estimate. If estimates are close, e.g. 3, 5, 5, 3, the team can quickly agree on a consensus, e.g. 5. If estimates vary wildly, e.g. 2, 5, 13, the highest and lowest estimators explain their reasoning first. The person with the high estimate might highlight hidden complexities or risks previously unconsidered by others. The person with the low estimate might point out a simpler solution, a misunderstanding of the request, or a way to reuse existing code. This discussion is the most valuable part of planning poker, as it uncovers forgotten details, clarifies assumptions, challenges perspectives, and leads to a deeper, shared understanding of the work. Repeat. After discussion, the team re-estimates. This process continues until a consensus or an acceptable range for a split estimate that the team agrees to proceed with is reached. Benefits: shared understanding. The discussion forces deeper thought about the scope and implications of a story, building a cohesive view across the team. Collective ownership. The estimate becomes a team estimate, not just one person's, fostering greater commitment to delivery. Exposes assumptions and risks. Divergent estimates often highlight unstated assumptions, misunderstandings, or potential problems that need to be addressed before development begins. Engaging and efficient. The game-like format can make estimation sessions more interactive and efficient than traditional, less structured meetings. Velocity, measuring team output and forecasting. Velocity is a key metric in Scrum and other Agile methodologies. It represents the amount of work a team can consistently complete within a single iteration sprint, measured in story points. How it's calculated. At the end of each sprint, the team sums the story points of all the user stories they successfully completed, meaning they meet the team's definition of done, e.g., coded, tested, deployed, documented. This sum is the team's velocity for that specific sprint. Over time, velocity is typically calculated as an average over several past sprints, e.g., the last 3 to 5 sprints. This averaging helps to smooth out fluctuations and provide a more stable forecast. Using velocity for forecasting. Once a team establishes a stable average velocity, it becomes a powerful empirical tool for forecasting future work. Release planning roadmapping. If you have a product backlog with estimated story points, you can divide the total estimated points for a given set of features by your average velocity to get a rough idea of how many sprints it might take to deliver that set of features. Example, product backlog of 100 estimated story points for the next major release. The team's average velocity is 20 points per sprint. Estimated duration for that release. 100 points / 20 points sprint equals 5 sprints. Setting realistic commitments, sprint planning. During sprint planning, a team uses its historical velocity to decide how many story points, or how many stories, they can realistically commit to trying to complete in the upcoming sprint. This helps prevent overcommitment and sets realistic expectations. Important caveats about velocity. Team-specific. Velocity is unique to a single team and its specific context. You cannot and should not compare velocities between different teams. A velocity of 20 for Team A doesn't mean they are faster or better than Team B with a velocity of 10. They simply have different calibrations for their story points. Not a performance metric. Velocity is a planning tool, not a measure of individual or team performance or efficiency. Gamifying velocity, pushing teams to increase it artificially, leads to inflated estimates, reduced quality by rushing done work, and team burnout. Affected by stability. Velocity is only reliable if the team composition, definition of done, working conditions, and external dependencies remain relatively stable. Significant changes in any of these areas can drastically impact velocity. Forecasting, not guarantee. Velocity provides a statistical forecast based on past performance. It's a highly useful indicator, but not a guarantee, especially if the nature of the work or team changes. Release planning versus sprint planning, different horizons. Agile estimation and planning occur at distinct levels of granularity, aligning with the principles of the cone of uncertainty. Release planning, long-term strategic. Focus. What major themes, epics, or a collection of features will be delivered in the next release, e.g., 3 to 6 months out? What is the overall goal or business outcome of this larger chunk of work? Estimates. Uses high-level story point estimates, often t-shirt sizes initially, then more refined story points for major pieces of functionality on the product backlog. This is where velocity is used for initial, broader forecasting. Output, a release roadmap or forecast indicating key features and potentially a target release date or number of sprints. It's a living plan, expected to adapt as new information emerges. Uncertainty, high. The cone of uncertainty is wide here. The intention is to provide a directional estimate for business planning, not a fixed commitment. Sprint planning, short-term tactical. Focus. What specific user stories can the team realistically complete in the next single sprint, typically 1 to 4 weeks? This is the tactical, detailed plan for the immediate future. Estimates. Detailed story point estimates for the user stories at the very top of the prioritized product backlog. These are the stories the team is ready to pull into the sprint. Often, these stories are broken down into specific technical tasks, which can be estimated in hours as they are well understood. Output. A sprint backlog, a list of user stories and associated tasks the team commits to for that specific sprint based on their capacity and velocity. Uncertainty. Relatively low for the committed sprint backlog as the team has fully understood the work and agreed upon its complexity. The product backlog, the heart of Agile planning. In Scrum, the product backlog is a single, prioritized, and ever-evolving list of everything that needs to be built into the product. It includes features, functions, non-functional requirements, enhancements, and bug fixes. It's continuously groomed or refined through an ongoing process of prioritization. Items are ordered by business value, risk, dependencies, urgency, and feasibility. Detailing, Higher priority items near the top of the backlog are more detailed, clearly defined, and have story points assigned. Items further down are less detailed and may only have t-shirt sizes or very rough estimates. Estimation. Story points are assigned during backlog refinement sessions, often using planning poker. The essence of Agile estimation. Agile estimation is not about being perfectly right up front. It's about being roughly right at the start and precisely right at the end. It embraces the reality of change and uncertainty by prioritizing learning, getting rapid feedback from delivered increments and adapting plans based on what is learned, focusing on flow, delivering valuable software iteratively and continuously, leveraging team wisdom, making estimates a collective responsibility, fostering transparent discussion and shared understanding, managing expectations, communicating estimates as forecasts and ranges, acknowledging the inherent uncertainty, revisiting the cone of uncertainty. While story points and velocity might seem abstract initially, they provide powerful tools for sustainable development, allowing teams to forecast and plan effectively without getting bogged down in the impossible task of perfect early predictions. By shifting focus from absolute time to relative size and learning incrementally, Agile teams can achieve greater predictability, deliver higher value, and build more robust software. In the next chapter, we'll explore some practical techniques that bridge the gap between traditional and Agile approaches, applicable in almost any software project context. Chapter 6. Practical techniques for any project. Relative sizing, analogy, and delve. While the previous chapters explored distinct methodologies, one rooted in traditional, upfront planning, and the other in Agile iterative processes, many valuable estimation techniques transcend these boundaries. These methods are practical, versatile, and can be adapted to fit various project contexts, team structures, and stages of the cone of uncertainty. Chapter 3. They often blend elements of human judgment with structured processes, aiming to make estimates more robust and reliable. Relative sizing, beyond just story points. We touched upon story points and t-shirt sizing in Chapter 5. The core philosophy of relative sizing, that it's easier to compare activities to each other than to assign an absolute time, is broadly applicable. Here, we delve deeper into how this relative thinking can be applied. T-shirt sizing, S, M, L, XL, XXL. T-shirt sizing is a qualitative, high-level estimation technique used for quickly sizing a large number of items, features, epics, user stories, when details are scarce, or when you need a rough order of magnitude estimate. How it works: instead of numbers, teams assign t-shirt sizes. The team collectively agrees on what constitutes an S, small, M, medium, L, large, and so on by relating them to known, completed work or establishing clear definitions. For example, an S is a task that feels like adding a simple field to a form. Process, often done in a group setting. Items are discussed briefly, and the team collaboratively assigns a t-shirt size. Dissension leads to discussion until a consensus is reached. Benefits: very fast for high-level backlog grooming or portfolio planning. Promotes shared understanding of relative effort. Excellent for very early stages of projects where uncertainty is high. Limitations: lacks the granularity for detailed sprint planning. Can be subjective if not calibrated within the team. Affinity estimation. Affinity estimation is another rapid, collaborative, and visual technique for relatively sizing a large number of user stories or backlog items. It leverages the team's collective intuition and facilitates quick consensus. How it works: preparation. Write each user story or backlog item on a separate index card. Silent relative sizing. Place the smallest known story on one end of a wall table and the largest known story on the other. Team members silently pick a card, read it, and place it relative to the others. There's no talking during this phase, forcing quick, intuitive decisions. Correction clustering. Once all cards are placed, the team walks through the sorted items. If anyone disagrees with a placement, they can move a card. Conversation is now allowed to clarify and justify moves. The team then clusters stories into agreed-upon buckets, e.g., t-shirt sizes or low-range, mid-range, high-range story point values. Assign point values. Assign actual story point values, e.g. 1, 3, 5, 8 to each bucket. Benefits: extremely fast for estimating large backlogs, can size hundreds of items in an hour or two. Highly collaborative. Visual and kinesthetic, which aids understanding and engagement. Reduces individual bias by forcing consensus through silent comparison. Limitations: best suited for high-level sizing. Not ideal for granular planning of individual tasks. Relies on the team's shared understanding of the relative scale. Analogy-based estimation, learning from the past. One of the most intuitive ways to estimate is to compare the current work to similar work done in the past. This is the essence of analogy-based estimation. Core idea: if you need to build X and you previously built Y and X is similar to Y, then X will likely take roughly as long as Y did. This relies on the premise that past performance is a reasonable indicator of future performance, assuming similar circumstances. How it works: identify similar past projects tasks. Search for projects or tasks that share key characteristics with the current one, e.g., similar technology, domain, team size, complexity, scope, customer type. Compare key attributes. Systematically compare the attributes of the new task project to the analogous ones. Are there differences in team experience, tool sets, available resources, non-functional requirements, or known risks? Adjust the estimate. Based on the identified similarities and differences, adjust the actual historical duration effort of the analogous project to derive an estimate for the new one. Prerequisites for accuracy: robust historical data. Access to accurate records of past project actuals, effort, duration, cost, even bug counts. Clear definitions, consistent definition of done and work breakdown in past projects. Similar context. The more truly analogous the past project task, the more accurate the estimate. Differences in team, technology, or environment can significantly skew results. Pros: data-driven. Leverages real historical data, making estimates more objective than pure guesses. Fast, can be very quick if good analogous data is readily available. Intuitive, easy for stakeholders to understand the basis of the estimate. Cons: uniqueness of software. As discussed in Chapter 1, software projects are often unique. Finding a truly analogous project can be challenging. Poor historical data. Many organizations lack reliable, detailed historical project performance data. Actuals are often skewed by the very problems the estimate is trying to solve. Context differences. Even seemingly similar projects can hide significant differences in environment, team capability, or external dependencies. Anecdote: the simple integration that wasn't. After successfully integrating with Payment Gateway A on a previous project, a team lead confidently estimated integrating with Payment Gateway B would take the same 3 weeks. It seemed analogous. However, Payment Gateway B, while offering similar functionality, had outdated documentation, a notoriously unhelpful support team, and required a security certification process that Gateway A did not. The analogous project ended up taking 6 weeks. The lesson: superficial resemblances can hide significant underlying differences. Dig deeper on the similar factors. Wideband Delphi method. Structured expert consensus. The wideband Delphi method is a group-based estimation technique designed to converge on a consensus estimate while minimizing the impact of individual biases, like anchoring or herd mentality, discussed in Chapter 2. It's a structured, iterative process that leverages expert judgment anonymously. Core idea: rather than having experts sit in a room immediately debating numbers, where dominant personalities can sway opinions, estimates are collected anonymously, discussed, and re-estimated in several rounds until a stable consensus is reached. How it works simplified. Coordinator. A facilitator, often the project manager or scrum master, oversees the process. Expert pool. A group of experts, developers, QAs, architects, business analysts, familiar with the work to be estimated. Initial estimate. Each expert independently and anonymously provides an initial estimate for the tasks using their chosen unit, e.g., hours, ideal days, story points. These are often 3-point estimates, O, M, P, to capture uncertainty. Consolidation and feedback. The coordinator collects all estimates, anonymizes them, and presents the aggregated results, e.g., average, median, range, outliers, back to the group. No names are attached to estimates. Discussion of outliers. The coordinator asks the experts with the highest and lowest estimates to briefly explain their reasoning behind their numbers. This discussion is crucial for surfacing assumptions, hidden complexities, or overlooked simplifications. They must justify their stance, but without identifying specific individuals. Re-estimation. After the discussion, experts re-estimate the same tasks independently and anonymously. The goal is to converge towards a narrower range due to shared understanding gained from the discussion. Repeat. Steps 4 to 6 are repeated for a few rounds until the estimates converge within an acceptable range, or the group agrees they cannot converge further. The final estimate is then agreed upon, often as the median or a weighted average of the last round's estimates. Benefits: reduces bias. Anonymity prevents dominant individuals from unduly influencing others and encourages honest, independent thought. Leverages collective wisdom. Benefits from multiple perspectives and expertise, leading to more comprehensive estimates. Forces discussion. The process of explaining outliers fosters critical thinking and uncovers hidden risks, assumptions, or misunderstandings. Increased buy-in. Since the team members participate in generating the estimate, they are more likely to commit to it. Cons: time-consuming, can take several rounds and active facilitation, more than a quick team discussion. Requires good facilitation. The coordinator needs to be skilled in drawing out explanations and managing the process. Depends on expert availability. Requires dedicated time from multiple busy experts. Parametric estimation. Statistical models for scale. Parametric estimation uses a statistical relationship between historical data and project parameters to calculate an estimate. It's often used for larger projects or portfolios when a reliable historical dataset exists. Core idea. If you know that, historically, every unit of a certain parameter, e.g., a function point, a line of code, a user story of a specific type correlates with a known amount of effort or cost, you can extrapolate that relationship to estimate new work. How it works: identify parameters, define specific project characteristics that correlate with effort cost, e.g., number of function points, lines of code, number of use cases, number of screens. Develop a model. Based on past projects, create a mathematical relationship, e.g., a regression analysis that links these parameters to the project's effort, cost, or duration. For instance, effort equals X number of function points plus Y. Apply to new project. Plug the parameters of the new project into the derived model to generate an estimate. Example model. The constructive cost model, COCOMO, is a well-known parametric model that relates project size, often in lines of code or function points, to effort and schedule, adjusting for factors like team experience, tool support, and required reliability. Prerequisites: large, consistent historical data set, crucial for building a statistically valid model. Data must be accurately collected and consistently defined across projects. Stable environment, more effective in organizations with standardized processes, technologies, and team structures. Pros: objective and data-driven, reduces subjectivity compared to purely expert-driven methods. Scalable, can be used to estimate very large projects or portfolios of projects. Defensible, estimates are based on statistical evidence from past performance. Cons: garbage in, garbage out, highly dependent on the quality and consistency of historical data. Less accurate for novel projects. Less effective for projects that are highly innovative, use new technologies, or deviate significantly from past patterns. Model complexity. Developing and maintaining accurate parametric models can be complex and require expertise. The versatility of the estimation toolkit. No single estimation technique is a silver bullet. The most effective approach often involves a combination of these methods, applied judiciously at different stages of a project and with varying levels of detail. T-shirt sizing or affinity estimation might kick off a portfolio discussion. Wideband Delphi could then be used for the larger, more uncertain features. As features become well-defined, story pointing, or analogy-based estimates might be used. The common thread among these practical techniques is their reliance on either clear past data or structured collaboration to counteract individual biases and shed light on hidden uncertainties. In the next chapter, we'll delve deeper into how to manage the inherent risks and uncertainties that these estimation techniques help to uncover. Chapter 7: Beyond the Number: Managing Risk and Handling Uncertainty. In the preceding chapters, we've dissected the challenges of software estimation, explored the human biases that skew our predictions, defined foundational concepts, and delved into various techniques, both traditional and agile. Yet, even the most meticulously calculated estimate remains a mere prediction about the future. The real world of software development is a messy, dynamic landscape, rife with unforeseen challenges, shifting priorities, and the ever-present shadow of the unknown unknowns. This is where the true art of predictability begins, moving beyond simply generating a number and proactively embracing the inherent uncertainty of software. It's about understanding, managing, and transparently communicating the risks that can derail even the best-laid plans. An estimate without an accompanying risk strategy is little more than a hopeful guess. The landscape of risk and uncertainty. Recall the cone of uncertainty from Chapter 3. Early in a project, estimates are broad ranges precisely because uncertainty is high. This uncertainty manifests as risk, a potential future event that, if it occurs, could have a negative impact on the project's scope, schedule, cost, or quality. Risks in software development can be broadly categorized. Technical risks: unforeseen problems with technology choices, integration challenges, performance bottlenecks, architectural complexity, or lack of critical expertise. Requirements risks: ambiguous, incomplete, or constantly changing requirements. Misunderstandings between stakeholders and the development team. Resource risks: unexpected loss of key personnel, unavailability of specialized skills, resource contention with other projects, or insufficient team bandwidth. External risks: vendor delays, regulatory changes, market shifts, or unforeseen legal issues. Organizational risks: lack of stakeholder support, unclear decision-making authority, poor communication channels, or conflicting priorities within the organization. Proactive risk management: a continuous process. Effective risk management isn't a one-time activity. It's a continuous, iterative cycle that ideally begins even before project estimation. Risk identification: brainstorming. Gather the project team and relevant stakeholders to openly discuss what could go wrong. Encourage a no bad ideas atmosphere. Checklists: use historical data or industry best practices, e.g., common pitfalls for certain technologies or project types, as a starting point. Assumptions analysis: every estimate is built on assumptions. What if those assumptions prove false? Each assumption is a potential risk. Expert interviews: talk to experienced individuals within or outside the organization who have worked on similar challenging projects. Root cause analysis: for risks that are identified, delve deeper to understand their underlying causes. This can uncover more fundamental issues. Risk assessment: once risks are identified, assess their potential impact and likelihood. Probability: how likely is this risk to occur? E.g., low, medium, high, or 10%, 50%, 90%. Impact: if this risk occurs, what would be its effect on the project? E.g., minor schedule delay, significant cost increase, loss of key features, reputational damage. Prioritization: many organizations use a simple matrix, probability X impact, to prioritize risks. Focus mitigation efforts on high probability, high impact risks first. Anecdote: the overlooked API update. During the planning for a new mobile e-commerce app, the team focused on familiar technical risks: performance, database scaling, and front-end animations. A junior developer, however, idly wondered during a brainstorming session, what if the third-party payment gateway updates its API without much notice? At the time, this was dismissed as a low probability. 6 months into development, the payment gateway indeed announced a deprecation of their old API, requiring a significant rewrite and retesting. What began as a low probability risk with the potential for medium impact proved costly. This highlights the importance of including all perspectives in risk identification and seriously assessing even seemingly minor risks, as a cumulative effect can be disastrous. Risk response mitigation planning. For each significant risk, plan how to address it. Avoid, change the project plan to eliminate the risk, e.g., choose a different technology. Transfer, shift the risk to another party, e.g., through insurance, outsourcing a risky component to a specialist vendor. Mitigate, take proactive steps to reduce the probability or impact of the risk, e.g., conduct a technical spike to test new technology, run a pilot program, acquire specialized training for the team. This is the most common and effective strategy. Accept, acknowledge the risk and its potential impact, but decide not to take any proactive action, often for low probability, low impact risks, or when mitigation costs exceed potential benefits. Have a contingency plan ready if it materializes. Building robust estimates, contingency, and buffers. Estimates should not be single, optimistic numbers. They must account for the inherent uncertainties and identified risks. This is where contingency and management reserves come in. Contingency, known unknowns. This is money or time set aside within the project budget or schedule to cover known risks that might materialize. For example, if you've identified a 30% chance that a specific API integration will take an extra week, you might add a day or two to the schedule for that task, or allocate funds to hire a consultant if needed. This contingency is often part of the project estimate and controlled by the project manager. It's allocated based on a detailed risk analysis. Management reserve unknown unknowns. This is a separate pool of money or time held by senior management, outside the project's original estimate. It's earmarked for unknown unknowns, those genuinely unforeseen issues that arise. You can't estimate these specifically because you don't know what they are, but experience tells you they will appear. This reserve is accessed only with higher-level approval and is a strategic mechanism to absorb truly unexpected shocks without derailing other projects. The key is to integrate these buffers into your estimates and communicate them. Instead of saying, "It will take 10 weeks," say, "We estimate 10 weeks, with a contingency of 1.5 weeks for identified risks, bringing our total forecast to 11.5 weeks to achieve a 90% confidence level." This is transparent and manages expectations effectively. Battling scope creep, the silent budget killer. Scope creep, as introduced in Chapter 3, is the incremental expansion of a project's requirements beyond its initially agreed-upon scope, without corresponding adjustments to budget, time, or resources. It's a leading cause of project failure and directly undermines estimations. Impact of scope creep. Each small addition, seemingly minor in isolation, aggregates to significant delays, cost overruns, and team burnout. It creates a death by 1,000 cuts scenario, eating away at project predictability. Strategies to combat scope creep. Clear scope definition. Start with a crystal clear, well-documented scope. This is your baseline. For Agile, this means well-defined user stories and a well-prioritized product backlog. Robust change control process. Establish a formal process for handling new requests. Any new feature or change must be evaluated for its impact on scope, schedule, and cost. This process should involve all key stakeholders. Prioritization. Continuously prioritize work based on value and urgency. In Agile, the product owner meticulously grooms the backlog to ensure only the most valuable items are estimated and developed. If new items are added, older, lower priority items must either be removed or the schedule budget adjusted. Saying no gracefully, and not yet. Project managers and product owners must have the courage to decline out-of-scope requests or, more productively, suggest them for a future phase or release. That's a great idea, but it's outside our current release scope. Let's add it to the backlog for consideration in Release 2. Transparent communication. Periodically and clearly remind stakeholders of the agreed-upon scope. Visualize it, e.g., burn-down charts for a fixed scope or burn-up charts for accumulated scope. Show them the impact of additional features on the schedule or budget. Transparent communication of uncertainty. This is perhaps the most critical aspect of moving beyond the number. Secrecy or overconfidence about estimates breeds distrust and disappointment. Communicate as ranges, not points, especially early in the project or for high-risk items. Instead of "it will take 8 weeks," say "it will take between 6 and 10 weeks with our best guess at 8. This aligns with the cone of uncertainty. State assumptions clearly. Every estimate has underlying assumptions. Make them explicit. This estimate assumes we have dedicated access to the legacy system documentation and that the third-party API performs as documented. This enables stakeholders to question these assumptions and reveals potential risks. Highlight identified risks. Present the prioritized list of risks along with the estimate. Explain the mitigation strategies. Our estimate is X, but we've identified Y and Z as key risks. We've allocated a contingency for Y, and for Z, we're taking action A. Use confidence levels. Express estimates with a confidence level. We are 80% confident this feature will be delivered within our 13-point estimate. This quantifies the uncertainty and informs decision-making. Explain the why, don't just present a number. Explain the thought process, the breakdown, the data used, and the discussions that led to the estimate. This builds credibility and helps stakeholders understand the complexities involved. Iterative updates. Communicate that estimates are living documents. As more information is gained, new requirements, technical discoveries, actual progress, estimates will be refined and updated. Project planning is dynamic, not static. Continuous learning and adaptation. Ultimately, mastering estimation is an ongoing journey. Every project provides valuable data points. Feedback loops. After each sprint or major deliverable, track actuals against estimates. This provides invaluable data for future projects and refines your team's velocity or historical metrics. Retrospectives. Regularly, e.g., at the end of each sprint or phase, hold retrospectives to discuss what went well, what could be improved, what should we stop doing. This includes analyzing estimation accuracy and identifying why actuals differed from estimates. Post-cultivate reviews. For larger projects, a comprehensive post-mortem or lessons learned session can be incredibly insightful. Analyze the initial estimates, the actuals, the risks that materialized or didn't, and the overall project predictability. Document these learnings. By proactively identifying and managing risks, building appropriate buffers into estimates, diligently controlling scope, and communicating uncertainty with transparency, organizations can shift from merely reacting to project crises to intelligently navigating the unpredictable waters of software development. This transforms estimation from a simple guessing game into a powerful tool for planning, risk mitigation, and building stakeholder trust, ultimately leading to more predictable and successful outcomes. In the next chapter, we'll delve into the practical planning process, how to translate these refined estimates into an actionable blueprint for development. Chapter 8, the planning process. From estimate to blueprint. So far, we've walked through the intricate art of software estimation. From understanding its inherent challenges and human biases to employing various techniques, both traditional and agile, for sizing work and managing risk. But an estimate, no matter how accurate or well-reasoned, is merely a number or a range. The real transformative power lies in converting these predictions into an actionable, living blueprint that guides your team from concept to delivery. This is the essence of the planning process. Planning in software development is not a one-time event. It's a continuous, multi-layered activity that adapts as new information becomes available and the project evolves. It moves from broad strategic vision to detailed daily tasks. One strategic road mapping, the North Star for your product. Before you ever estimate a single user story, you need a high-level strategic roadmap. This is the product's long-term vision, outlining where the product is headed over the next 12 to 24 months. It's a living document, not a rigid schedule, focusing on solving user problems and achieving business outcomes. Purpose: to align all stakeholders on the product's direction, key initiatives, and major milestones. It answers the why and the what at a high level. Content typically includes vision statement, the overarching goal, strategic themes goals, high-level objectives, e.g., improve user retention, expand into new markets. Major initiatives epics, large bodies of work or significant features grouped under themes. These might be initially sized with t-shirt sizes, chapter 6, or very rough story points to provide a crude sense of scale. Rough timelines, often shown as quarters or major releases, indicating when major themes are expected to be addressed. Connection to estimation. The roadmap uses the earliest, broadest estimates, the wide end of the cone of uncertainty, Chapter 3, to guide strategic investment decisions. It helps leadership decide if a project is worth pursuing, given its perceived size and business value. Changes here have significant impact, so they must be carefully considered. 2. Release planning. Defining the next major step. Release planning defines what a specific version of your software will contain and when it is expected to be delivered. It typically looks at a horizon of a few weeks to a few months. Different organizations might define release as a major version, e.g., v2.0, a major feature set, or simply a collection of sprints aimed at a common goal. Purpose. To define the scope of the next significant chunk of value the team will deliver to users, and to set a realistic target date for that delivery. Process, Agile context. Prioritized product backlog. The product owner ensures the product backlog, Chapter 5, is well-groomed, with top priority items detailed and estimated in story points. Team velocity. The development team reviews its average historical velocity, Chapter 5, understanding its capacity. Scope versus time. The team, product owner, and stakeholders collaborate to select a set of features from the backlog that can realistically be delivered within a desired number of sprints, or to determine how many sprints are needed for a desired set of features. This is where velocity becomes critical for forecasting. Dependencies. Identify any key dependencies, e.g., external integrations, other teams, third-party libraries, that must be resolved for this release. Refinement. The release plan is refined as sprints progress and new information emerges. Requirements might be split, reprioritized, or deemed out of scope for the current release. Output. A list of features epics targeted for the release, a predicted number of sprints, and a target release date, which is a forecast, not a fixed commitment. Connection to estimation. This phase directly leverages story point estimates and team velocity to make data-driven predictions about scope and duration. 3 iterations sprint planning. The tactical game plan. Sprint planning is the most granular level of formalized planning in Agile methodologies, though similar daily planning happens in traditional projects. It's the team's commitment for the next 1 to 4 weeks. Purpose, to define what the team will accomplish in the upcoming sprint and how they will accomplish it. Process, product backlog review. The team pulls high-priority, ready-to-develop items from the top of the product backlog. These are usually well understood, clearly defined, and already estimated in story points. Sprint goal definition. The team and product owner collaboratively define a clear, concise sprint goal, e.g., enable users to create an account and log in. Capacity check. The team assesses its capacity for the sprint, factoring in vacations, holidays, and planned training. Commitment to stories. Based on capacity and historical velocity, the team selects a realistic set of stories to commit to for the sprint. Task breakdown. The team then breaks down each selected user story into smaller, actionable technical tasks, e.g., design database schema for user table, develop login API endpoint, write unit tests for registration form. These tasks are often estimated in hours, as they are now concrete and well-defined. Output. A sprint backlog, the list of user stories and associated tasks for the current sprint, along with the sprint goal. This is the team's short-term commitment. Connection to estimation. This phase uses the most refined estimates. While story points guide the selection of stories, the task breakdown might involve hour estimates. Key elements of an effective planning process. Regardless of the planning level, several elements are crucial for turning estimates into an effective blueprint. Definition of done, do D. A clear, agreed-upon definition of done is paramount. Without it, developers might consider a task complete when the code is written, while QA expects testing and deployment to production. Purpose. Ensures consistent quality and completeness. Prevents partial work from being deemed finished. Content. A checklist of criteria that a user story or task must meet to be considered done. Examples include Code reviewed, unit tests passed, integrated with main branch, QA tested, functional and non-functional, deployed to staging, acceptance criteria met, documentation updated. Impact on estimates. A robust DoD means estimates must account for all required activities, not just coding. Misalignment on DoD frequently leads to underestimation. Dependency management. Dependencies are tasks or pieces of work that rely on others. Ignoring them can lead to significant delays, regardless of individual task estimates. Identification. At all levels of planning, roadmap, release, sprint, explicitly identify internal e.g. Front-end code needs API to be ready and external e.g. waiting for third-party vendor, hardware delivery, dependencies. Visualization. Tools like Gantt charts, from CPM, Chapter 4, dependency maps, or even simple swim lanes on a Kanban board can help visualize these relationships. Mitigation. Plan around them. Can tasks run in parallel? Do we need to engage another team or vendor earlier? Can we mock data to unblock progress? Communication. Constantly communicate dependency status with affected teams and stakeholders. Resource allocation. Planning involves ensuring the right people with the right skills are available at the right time. Balancing workload. Distribute tasks fairly across the team, leveraging individual strengths and promoting cross-functional learning. Avoid overallocating individuals. Skill gaps. Identify where specialized skills might be needed, e.g., new technology, complex algorithms, and plan for training, hiring, or external consultation. Tooling and environment. Ensure necessary software, hardware, and development testing environments are prepared and accessible. Monitoring progress. Steering the ship. Once the plan is set in motion, continuous monitoring is essential to ensure you're on track, identify deviations early, and adapt. Burn-down charts, primarily used in Agile sprints or releases. They show the remaining work, e.g., story points or tasks, against the time remaining. A descending line indicates progress. If the actual burn-down line is above the ideal line, the team is behind schedule. Burn-up charts, similar to burn-down, but they show the accumulated completed work over time. Crucially, they also show the total scope. This is very useful for visualizing scope creep, as you can see if the total scope line is increasing while the completed work line is rising. Kanban boards, visual representations of workflow. Tasks move from to-do to in progress to done. They highlight bottlenecks and encourage continuous flow, providing real-time status updates at a glance. Daily stand-ups or similar syncs. Short, daily team meetings where each member briefly states what they did yesterday, what they plan to do today, and any impediments. This helps the team self-organize and identify blockers early. Definition of ready doer. Before a story or task even enters a sprint, having a definition of ready checklist ensures it's well understood, feasible, and ready for development, minimizing mid-sprint confusion and re-estimation. Adapting the plan. Embrace change. The most critical aspect of any plan is its ability to adapt. As discussed at length in Chapter 7, predictability doesn't mean perfect adherence to an initial guess. It means consistent, timely delivery based on the best current information, even if that means shifting the scope or timeline. Regular reviews. Conduct regular sprint reviews DMOS with stakeholders to get feedback and adapt the plan. This is your opportunity to show progress, discuss challenges, and realign expectations. Retrospectives. After each sprint or major phase, conduct a team retrospective to reflect on what went well, what could be improved, and what should we stop doing. This learning specifically includes the planning and estimation process itself, identifying how to make future forecasts more accurate. Open communication. Maintain open, honest communication with all stakeholders, Chapter 7. If an estimate needs to change, explain why transparently, backed by data and insights. It's far better to deliver a realistic update than to let negative surprises fester. By diligently practicing multi-layered planning, establishing clear definitions, proactively managing dependencies, and continuously monitoring and adapting, you transform a set of estimates into a dynamic, living blueprint. This strategic approach guides the team, aligns stakeholders, and significantly increases the likelihood of delivering successful software projects, even in the face of inevitable change. In the next chapter, we'll explore the tools that can support this intricate process. Chapter 9, Tools of the Trade, Software for Estimation and Planning. In an increasingly complex and interconnected software development landscape, relying solely on whiteboards, spreadsheets, or individual memory for estimation and planning is often insufficient. While the principles and techniques discussed so far are paramount, robust software tools can significantly enhance the effectiveness, transparency, and efficiency of your estimation and planning processes. These tools don't estimate for you, nor do they replace critical thinking or human judgment, but they can provide powerful support for structuring work, tracking progress, visualizing data, and facilitating collaboration. The role of software tools. Broadly, software tools for estimation and planning serve several key functions. Centralized Information Hub provide a single source of truth for requirements, estimates, tasks, and progress. Workflow management facilitate the breakdown of work, assignment of tasks, and tracking of progress through various stages. Visualization and reporting generate charts, e.g., burn down up, reports, and dashboards to show project status, identify trends, and communicate progress to stakeholders. Collaboration enable real-time communication, comment threads, and shared views for distributed teams. Historical data collection automatically log task durations, completion rates, and other metrics, which is invaluable for refining future estimates. Analogy-based, parametric, velocity chapters 5 and 6. Dependency management help map out and track relationships between tasks and teams, Chapter 8. Choosing the right tools depends on your methodology, agile, traditional, hybrid, team size, organizational culture, budget, and specific needs. Categories of tools and their applications. Let's explore some common categories of software tools and how they support estimation and planning. Project Management Information Systems, PMIS. These are comprehensive platforms designed to support the entire project lifecycle, often with a strong emphasis on traditional project management principles, WBS, Gantt charts, resource allocation. Examples: Microsoft Project, Primavera P6, Smartsheet. Estimation and planning support, WBS creation, allows building hierarchical work breakdown structures, Chapter 3, to decompose projects into manageable tasks. Gantt charts and CPM visualizes tasks, dependencies, and timelines, automatically calculating critical paths, Chapter 4. Resource management assigns resources to tasks, identifies overallocations, and helps balance workloads. Budgeting integrates effort estimates with labor rates to calculate project costs. Baseline management allows setting a baseline plan and tracking variances against it. Best for large, complex projects with stable requirements and a need for detailed, upfront planning and strong dependency management. Often used in engineering, construction, and waterfall-style software development or long-term strategic planning. Agile project management tools/work management platforms. These tools are specifically designed to support iterative and incremental development methodologies, focusing on transparency, collaboration, and continuous delivery. Examples: Jira, Azure DevOps, Asana, Trello, Monday.com, ClickUp. Estimation and planning support, product backlog management, facilitates creation, prioritization, and grooming of user stories, epics, and features. Story pointing allows assigning story points, Chapter 5, to backlog items. Some integrate with planning poker plugins. Sprint planning supports pulling stories from the backlog into sprints, defining sprint goals, and breaking stories into tasks. Kanban boards, visual display of workflow, enabling teams to track tasks from to-do to done, identifying bottlenecks. Velocity tracking automatically calculates and displays team velocity, Chapter 5, based on completed story points. Burn down, burn up charts provides real-time visual progress against targets and scope changes, Chapter 8. Collaboration features, discussions, attachments, and historical audit trails on each work item. Best for Agile teams, Scrum, Kanban, hybrid approaches, and organizations that prioritize flexibility, iterative development, and continuous feedback. Specialized estimation software. While less common as standalone tools today, some software focuses purely on quantitative estimation models. These often tie into function point analysis or parametric models. Examples: SEER by Galarath, COCOMOII implementations exist, not a single commercial product. Estimation and planning support, function point counting, tools to aid in systematically counting function points based on requirements. Parametric modeling, implementations of models like COCOMOII, allowing users to input project parameters and generate effort, schedule, and cost estimates based on historical data and calibrated algorithms. Risk analysis. Some provide Monte Carlo simulations for more advanced risk analysis, yielding probabilistic estimates. Best for large enterprises, government contracts, or organizations that require highly data-driven, defensible estimates for fixed-price contracts or very long-term planning, and have extensive calibrated historical data. They are less about day-to-day project management. Spreadsheets and spreadsheet-like platforms. The ubiquitous spreadsheet remains a powerful, flexible, and accessible tool for many estimation and planning tasks, especially for smaller teams or early-stage projects. Examples: Microsoft Excel, Google Sheets, Airtable, LibreOffice Calc. Estimation and planning support. Custom templates can be customized to create unique estimation worksheets, e.g., 3-point estimation calculations, PERT calculations. Simple task tracking, basic lists of tasks, assignments, and due dates. Basic data analysis can be used to manually track velocity or generate simple charts. Ad hoc calculations, ideal for what-if scenarios and quick calculations. Best for small teams, startups, ad hoc analysis, or when specialized tools are cost-prohibitive. They offer unparalleled flexibility but can quickly become unwieldy for larger, more complex projects if not managed rigorously. Best practices for using tools effectively. Simply acquiring a tool doesn't guarantee better estimates or planning. How you use it is critical. Choose the right tool for your context. Don't force a square peg into a round hole. A large enterprise might need a PMIS, while an agile startup thrives on Jira. Align tool capabilities with your team's methodology and needs. Keep it simple. Start with the core features your team needs. Overly complex configurations can lead to resistance and underutilization. Tools should reduce, not increase, administrative burden. Ensure data quality and consistency. Garbage in, garbage out. If your team isn't diligent about updating task statuses, entering estimates, or closing out work, the reports and forecasts from the tool will be inaccurate. Regularly review and adapt. Tools should evolve with your process. Periodically review how the team is using the tool. Are there features that are being underutilized? Are there pain points that could be addressed by a different configuration or a new tool? Integrate where possible. Many modern tools offer integrations with other systems, e.g., source code repositories, communication tools, CI/CD pipelines. This can automate data flow and provide a more holistic view of the development process. Don't over-rely on the tool. Remember, the tool is a support system, not a replacement for human judgment, communication, or critical thinking. No tool can estimate unknown unknowns or resolve interpersonal conflicts. The tool displays data, humans interpret and act on it. Training and adoption. Invest in proper training for your team. Ensure everyone understands how to use the tool effectively and why it's important for project success. Address resistance through education and demonstrating value. By thoughtfully selecting and diligently utilizing the right software tools, organizations can transform their estimation and planning from a collection of isolated guesses into a transparent, data-driven, and continuously improving process. These tools empower teams to visualize their progress, manage complexity, and communicate effectively, ultimately building a more predictable path to successful software delivery. In our final chapter, we will discuss the cultural shifts and continuous learning necessary to truly cultivate a culture of predictability. Chapter 10: Cultivating a Culture of Predictability. Communication, Learning, and Improvement. We've journeyed through the intricacies of software development estimation and planning, dissecting the challenges, exploring myriad techniques, and even examining the tools that can aid our efforts. Yet all this knowledge, all these methodologies, and all the sophisticated software in the world will fall short if the underlying culture of the organization isn't conducive to predictability. Mastering estimation and planning isn't merely about crunching numbers or mastering a new workflow. It's fundamentally about fostering a healthy, transparent, and learning-oriented environment where predictability flourishes as a natural outcome, rather than being a constant struggle. This final chapter emphasizes the human and organizational elements that are the bedrock of consistent, reliable software delivery. 1. The bedrock of trust. Psychological safety. Reliable estimates begin with honest estimates. Honest estimates, in turn, depend heavily on psychological safety, a shared belief that the team is a safe place for interpersonal risks. If team members fear reprisal, ridicule, or punishment for delivering bad news, e.g., a higher estimate than desired or stating technical difficulties frankly, they will inevitably sugarcoat estimates, underreport problems, and avoid critical discussions. Foster openness. Leaders and managers must actively solicit and genuinely value diverse opinions, even those that challenge the status quo or reveal uncomfortable truths. Embrace what-if scenarios. Create an environment where asking probing questions, what if this goes wrong? And exploring worst-case scenarios is seen as prudent risk management, not negativity. Separate the messenger from the message. Never shoot the messenger. When a team member reports a delay or a higher estimate, focus on understanding the root cause and finding solutions rather than assigning blame. Celebrate learning, not just success. Acknowledge that failures and misjudgments are inevitable. The focus should be on learning from them to improve future processes, not on finding a scapegoat. 2. Relentless focus on communication and transparency. Poor communication is the silent assassin of project predictability. Without clear, consistent, and transparent communication, assumptions fester, expectations diverge, and even the best estimates become irrelevant. Clear and consistent messaging. Ensure that estimates, their underlying assumptions, and the associated risks, Chapter 7, are communicated clearly to all stakeholders. Avoid jargon. No surprises culture. Strive for a no surprises culture. If a delay or a change in estimate is anticipated, communicate it early and often, explaining the why. This builds trust, even when the news isn't ideal. Visualize progress. Use burn-down, burn-up charts, Kanban boards, and dashboards, Chapter 9, to make project progress and potential issues visible to everyone. Visuals are powerful communication tools. Active listening. Encourage active listening during estimation and planning sessions. This isn't just about hearing words, but about truly understanding the underlying meaning, concerns, and unstated assumptions. Stakeholder engagement. Actively involve stakeholders in the estimation and planning process where appropriate, e.g., during sprint reviews, backlog grooming. This helps them understand the complexities and builds shared ownership of the plan. 3. Embrace continuous learning and adaptation. Predictability isn't a destination, it's a journey of continuous improvement. Every project, every sprint, every task is a learning opportunity. Retrospectives and postmortems. Make time for regular, structured reflection. Sprint retrospectives, Agile, a dedicated meeting at the end of each sprint for the team to inspect how they are working and identify improvements. This should include analysis of estimation accuracy. Project postmortems / lessons learned sessions. For larger projects, a more comprehensive review of the entire project lifecycle. Compare initial estimates to actuals, discuss what went well, what went wrong, and what insights can be applied to future projects. Data-driven feedback loops. Develop systematic ways to collect data on actual effort, duration, and scope. Use this data to calibrate and refine your team's velocity, Chapter 5. Update your historical databases for analogy-based estimation, Chapter 6, and refine parametric models. Over time, this makes estimates increasingly accurate. Knowledge sharing. Document and share lessons learned. Create an internal wiki or knowledge base of common challenges, successful solutions, and estimation guidelines. When a new developer joins, they shouldn't have to relearn all the hard lessons of the past. Training and development. Invest in training for your team members on new technologies, project management best practices, and, crucially, estimation techniques. Keep skills sharp and up to date. For leadership's role, setting the tone. Ultimately, the culture of an organization and its approach to predictability is shaped by its leadership. Lead by example. If leaders demand unrealistic estimates, they will get them. If they punish transparent reporting of delays, they will get hidden problems. Leaders must model the desired behavior, embrace uncertainty, communicate honestly, and support teams in their efforts to improve. Prioritize clearly. Unclear or constantly shifting priorities are a major source of unpredictability. Leaders must provide a clear vision and stable strategic direction, allowing teams to focus their efforts. Protect the team. Shield teams from external pressures and unreasonable demands. Empower product owners and project managers to negotiate scope and timelines realistically. Invest in tools and training. Demonstrate commitment by providing the necessary resources for effective estimation and planning. Reward honesty and learning. Recognize and reward teams and individuals who provide honest estimates, communicate risks early, and contribute to the collective learning, rather than just those who hit seemingly impossible deadlines. The ongoing quest for predictability. No software project will ever achieve perfect predictability. The inherent complexity, constant change, and human element ensure that. However, the objective isn't to eliminate uncertainty, but to manage it intelligently and communicate it transparently. The software blueprint has provided you with a comprehensive toolkit, from understanding fundamental concepts and human biases to exploring various estimation techniques and planning strategies, all supported by appropriate tools. But the ultimate success of these tools and techniques rests on the foundation of a robust organizational culture. By fostering psychological safety, championing transparent communication, embracing continuous learning, and demonstrating consistent leadership, any organization can transform its approach to software development. It can move from a state of constant firefighting and reactive adjustments to one of proactive navigation, thoughtful decision-making, and predictable delivery. The journey to mastering estimation and planning is an ongoing one, continually refined by experience, feedback, and a commitment to excellence. May your crystal ball become a little clearer with each project you undertake.